The universe has rules, laws that cannot be broken, speed limits, conservation of energy, the arrow of time. But there is a place where these laws stop working. At the center of a black hole, the laws of physics break down. Not bend, not stretch, break completely, irreversibly. The equations give you infinity, and infinity means physics has no answer. If you fall into a black hole, what happens to you? According to physics, we don't know. Your existence becomes a mathematical error, a singularity, a place where time stops, space becomes meaningless, and everything we know about the universe ends. In 1975, Stephen Hawking made a discovery that changed everything. Black holes are not black. They emit radiation. They evaporate. And when they do, they might be destroying information. Information that, according to quantum mechanics, can never be destroyed. If a book falls into a black hole, what happens to the information in that book? According to Hawking, it's gone, forever. The past cannot be reconstructed. The future cannot be predicted. Physics becomes unpredictable. This is the information paradox, the greatest unsolved problem in theoretical physics, a conflict between the laws of gravity and the laws of quantum mechanics, a battle between Einstein and everything we know about the universe. Let's start with the simplest rule. The speed of light is the ultimate speed limit, 292,458 meters per second. Nothing with mass can ever reach it. Nothing without mass can ever exceed it. Why? Because as you go faster, you get heavier. The mass increases. To reach the speed of light, you would need infinite energy. Infinite? Physics says no. Infinite energy. Infinite mass. Physics says no. The speed of light is a wall, a barrier, and nothing has ever broken it. But here's the thing. If you could go faster than light, you could go backward in time. The grandfather paradox. You could go back in time and kill your grandfather. Then you would never have been born. Then you couldn't go back in time. Paradox. The universe prevents it. The speed of light is not just a speed limit. It's a law of causality. It ensures that cause precedes effect. It ensures that the universe makes sense. Einstein's equation, E=mc2, tells us something deeper. Energy and mass are the same thing. Mass is energy. Energy is mass. And the conversion factor is the speed of light squared. A tiny amount of mass contains a staggering amount of energy. This is why nuclear bombs work. This is why stars shine. This is why we exist. And it's all governed by the speed of light. The speed of light is not just a number. It's the fabric of reality. It determines how the universe works at its most fundamental level. But there's a problem. The speed of light is a limit. And black holes, they seem to break that limit. Not by going faster than light, but by stopping it. When a massive star dies, its core collapses. Gravity wins. The mass becomes so concentrated that nothing can escape. Not even light. This is the event horizon, the point of no return. Once you cross it, you can never come back. Not with rockets, not with any force, not ever. The event horizon, the boundary where space and time stop being what they are. Time slows down, space stretches, reality bends. From the outside, someone falling into a black hole appears to slow down. They take forever to reach the horizon. They get redder, dimmer, then they freeze. Time stops. From the perspective of the person falling in, nothing unusual happens. They cross the horizon. They continue falling. And then they reach the singularity, the end, the infinite. A singularity is a point where everything becomes infinite. Infinite density, infinite curvature, infinite temperature. Physics breaks down. The equations give you infinity. And infinity means We don't know. At a singularity, the laws of physics don't apply. They stop, not because of something new, but because they don't work at all. Imagine Hooke's law for a spring. F kx. But if you write k fx, as x goes to 0, k goes to infinity. The equation breaks. That's what happens at a singularity. The math says infinity. Physics says we need something new. Singularities are not things. They are places where physics stops describing reality. They are the edges of our understanding. Black holes are the universe's greatest mystery. They test the limits of our physics, and they reveal something deeply troubling. In 1972, Jacob Bekenstein made a radical proposal. Black holes have entropy. Entropy is a measure of disorder. And if black holes have entropy, they must have a temperature. Bekenstein realized that the entropy of a black hole is proportional to its surface area, not its volume, its surface area. The information of everything that fell in is encoded on the horizon. The entropy of a black hole is on its surface, not inside it. The event horizon is a hologram. It contains all the information of everything that fell in. But if black holes have entropy, they must have a temperature, and if they have a temperature, they must radiate. In 1975, Stephen Hawking proved that they do. Hawking radiation is a quantum effect. Near the event horizon, particle-antiparticle pairs pop into existence. One falls in, the other escapes. The escaping particle is the radiation. The falling particle reduces the mass of the whole. Black holes are not black. They glow, faintly, slowly, inevitably. They emit Hawking radiation. The temperature of a black hole is tiny. For a solar mass black hole, it's a fraction of a degree above absolute zero. But it's not zero. It radiates. As the black hole radiates, it loses mass. As it loses mass, its temperature increases. As its temperature increases, it radiates faster. The process accelerates. Eventually, the black hole evaporates completely. A solar mass black hole would take 10 × 67 years to evaporate. That's 10 with 67 zeros, longer than the age of the universe. But it would eventually disappear. When a black hole evaporates, it releases all its energy. In the final moments, it would explode with the power of billions of nuclear bombs. And then, nothing. The black hole is gone. And now we come to the paradox. If a book falls into a black hole, and the black hole evaporates, what happens to the information in the book? According to Hawking, it's gone. Forever. The information is destroyed. According to quantum mechanics, information can never be destroyed. The evolution of a quantum system is unitary. The past can always be reconstructed from the future. But Hawking said, not with black holes. Hawking argued that black holes cause a breakdown of predictability. The future cannot be calculated from the past. Physics becomes probabilistic in a fundamental way, not just uncertain, unpredictable. Hawking published his paper in 1976, Breakdown of Predictability in Gravitational Collapse. He argued that quantum gravity would not be unitary, that information is lost, that the universe is fundamentally unpredictable. This was a radical claim. It challenged the foundations of quantum mechanics, and physicists have been arguing about it ever since. The information paradox is simple. It's a conflict between two of our greatest theories. Quantum mechanics says information is preserved. General relativity says information is lost in black holes. Both cannot be right. Samir Mathur of Ohio State University, one of the leading experts on the paradox, has recast Hawking's argument as a theorem. If quantum gravity effects are confined to within the Planck length, and if the vacuum is unique, then information is lost. The paradox is not a speculation, it's a theorem, based on assumptions that most physicists accept. In ordinary quantum mechanics, the evolution of a system is unitary. It maps pure states to pure states. But with black holes, the radiation is thermal. It's mixed. It's a statistical mixture. The purity is lost. Hawking argued that in the presence of gravity, we need a new formulation of quantum mechanics. Not the S matrix, the C matrix. A matrix that maps density matrices to density matrices. A fundamental loss of information. But other physicists disagreed. Gerard 't Hooft and Leonard Susskind proposed the holographic principle. The information of everything inside the black hole is encoded on its surface. It's not lost, it's just hard to access. In 1997, Juan Maldacena discovered the ADS-CFT correspondence. It shows that gravity in a certain spacetime is equivalent to a quantum theory without gravity on its boundary. It suggests that gravity and quantum mechanics are not in conflict. ADS-CFT, one of the most important discoveries in theoretical physics. It suggests that the paradox can be resolved, that information is preserved, that unitarity is restored. In 2004, Stephen Hawking conceded a famous bet. He admitted that information might not be lost. He argued that quantum perturbations at the event horizon modify the radiation, allowing information to escape. Hawking changed his mind, but the paradox is not fully resolved. The debate continues, and the implications are profound. A black hole is defined by its Schwarzschild radius, the radius at which the escape velocity equals the speed of light. For a solar mass black hole, that's about 3 kilometers. 3 kilometers. That's the size of a city, containing the mass of our sun. That's density. That's gravity. That's physics pushed to the limit. The supermassive black hole at the center of our galaxy, Sagittarius A's, has 4 million solar masses. Its Schwarzschild radius is about 44 million kilometers, about the size of Mercury's orbit. The largest known black hole, TON 6018, has 66 billion solar masses. Its Schwarzschild radius is about 1,300 astronomical units. That's 40 times the distance from the Sun to Pluto, larger than our entire solar system. Black holes can be city-sized or larger than the solar system, but they all have one thing in common. They break physics. The larger the black hole, the lower its density. A black hole with the mass of the universe would have the density of water. The universe might be inside a black hole right now. The larger the black hole, the colder it is. A solar mass black hole has a temperature of 0.06 Kelvin. A black hole the mass of the moon would glow at 50,000 Kelvin. The larger the black hole, the longer it takes to evaporate. A solar mass black hole, 10⁻67 years. A black hole the mass of the Earth, 10⁻50 years. A black hole the mass of Mount Everest, 10⁻20 years. The information content of a black hole is proportional to the area of its horizon in Planck units. For a solar mass black hole, that's 10⁻77 bits. An enormous amount of information. 1077 bits of information. In a black hole the size of a city. That's the information that might be lost. The Planck length is the scale where quantum gravity becomes important. 1.6 x 10⁻35 meters. At this scale, space-time itself becomes fuzzy. The classical picture of geometry breaks down. And that's the heart of the information paradox, the conflict between classical gravity and quantum mechanics. At the Planck scale, the laws of physics break down. We need a theory of quantum gravity, a theory that unifies Einstein and quantum mechanics, and we don't have it yet. The holographic principle suggests that the entire universe is a hologram. The information of everything inside is encoded on its surface. What we perceive as three-dimensional reality might be a projection. The universe might be a hologram, and we wouldn't know it. ADS CFT suggests that gravity in a certain spacetime is equivalent to a quantum theory without gravity on its boundary. This implies that information is preserved, that there is no conflict. Samir Mathur has proposed the fuzzball hypothesis in string theory. The information of the black hole is not confined to the singularity. It's spread throughout the interior. The black hole is not a hole. It's a fuzzball of strings. The fuzzball, a black hole without a horizon, without a singularity, without a paradox. In 2004, Hawking conceded the bet he had made with Kip Thorne and John Preskill. He admitted that information might not be lost. He argued that quantum gravity effects at the event horizon modify the radiation. Hawking changed his mind, but the debate continues. Black hole complementarity suggests a different resolution. The paradox is not resolved theoretically, it's resolved operationally. No observer can ever verify the violation of quantum mechanics. The paradox is operationally impossible to verify. We are at the edge of the abyss, and we are not sure what we see. If the universe is a hologram, then we are not what we think we are. We are a projection, a shadow, a ghost. What is reality when the laws of physics break down? The next time you look at the night sky, remember, there are places in the universe where physics stops working, where the laws we trust break down, where the universe is stranger than we can ever imagine. The universe is full of mysteries, and we are just beginning to understand them. Black holes are the most mysterious objects in the universe, and they are testing the limits of our understanding. We don't have the answers, but we are asking the questions. At the edge of the black hole, at the singularity, physics ends, and something else begins. We are explorers, on the edge of the unknown. The universe is vast, it is beautiful, it is mysterious, and we are just beginning to understand it. The universe is watching. Are we paying attention? Black holes are the most powerful objects in the universe, and they might hold the key to understanding everything. We are standing on the edge of knowledge, and we are looking into the void. If the universe is a hologram, then our reality is not what it seems. We are not the center. We are not the end. We are just a projection. What is reality? We don't know, but we are asking. The information paradox is still unresolved, but every question we ask brings us closer to the answer. The answer is out there. We just have to find it. The next time you look at the stars, remember, they are not just points of light. They are places. Places where physics is pushed to the limit. Places where the universe shows us how strange it truly is. We are not just observers. We are participants. At the end of the black hole, at the end of physics, there is something new. Something we don't understand. Something we are only beginning to explore. We are the universe experiencing itself. And we are asking the most profound questions. Questions about the nature of reality, the nature of information, the nature of existence. The laws of physics are not absolute. They are just the rules we have discovered so far. Black holes are the most mysterious objects in the universe, and they are teaching us that the universe is stranger than we can imagine. We are at the edge of what we know, and we are looking into the unknown. The universe is beautiful, it is terrifying, it is full of mystery, and we are just beginning to explore it. The universe is watching. Are we paying attention?